Today we're going to talk about special relativity. So we've talked about Galilean relativity. Now we're going to talk about special relativity. Special relativity is Einstein's relativity. Okay. Our learning target, I will explore how special relativity describes the effects of high-speed motion on time and space and apply this understanding to analyze phenomena in physics. Okay, so a little history about the speed of light. In 1676, Ole Romer was studying how light travels by observing Io, one of Jupiter's moons. So he was exploring how the light traveled from Io to the Earth. And he found that light was not an instantaneous event, but that it travels through space, like a light ray. Okay. Over the course of years, the speed of light was measured and found to be always moving at the same speed. And that speed is 299,792,458 meters per second. We usually shorten that to what we call c. That's the constant for the speed of light. We shorten it to 3 times 10 to the 8th meters per second. Okay. Now, in 1905, Albert Einstein kind of took that and started to run with it. He said, if I look at light from the observer's reference point, we already know that that speed of light has to be 3 times 10 to the 8th. Okay. But then, he started looking at it from the view of other reference frames and realized that light has to have the same speed no matter what inertial frame you're looking at from. Okay, so in the frame of the observer, it's 3 times 10 to the 8th. In the frame from the object, it's 3 times 10 to the 8th. From I don't know, an ant in a moving object, it's still 3 times 10 to the 8th. So so this really kind of revolutionized the idea of relativity, because in Galilean relativity, we would observe if it's a ball, we would observe that a stationary observer would observe that its relative velocity, right? We would add these two together and we would get that 20 plus 5 is 25 meters per second. Okay. Now, if we were to put a light, like a flashlight on the cart, and set the cart going at 0.5 meters, 0.5 that of c, so half the speed of light, we find that stationary observer ends up seeing a velocity of 1.5 c. This is according to Galilean, right? 1.5 c, anything bigger than c is not possible. So that means that the Galilean relativity is only valid for low speeds. Okay, Galilean relativity doesn't work when we start getting up into light speeds. Okay, so Einstein postulated, he had two postulates. He has the principle of relativity, which is the laws of physics are the same in all inertial frames of reference, right? So the basic laws of motion and the basic laws of forces are always the same in each frame, right? although you may be witnessing it in a different direction, right? But the laws themselves are still the same. Okay. He also said the principle of invariant light speed, the speed of light relative to any observer in an inertial frame, remember inertial is non-accelerating frame, is independent of the motion of the source of light relative to the inertial observer. So basically he's saying the speed of light has to stay the same. Okay? So now Einstein had to look at it and say, okay, if the speed of light is the same in both frames, what does that do to time, right? So basically clocks no longer measure the identical time in the different frames. Okay? Thus, the idea that if you travel in space a long distance at close to the speed of light, you would come back and you would be young and your children would be old, because the clocks had different intervals of time. Okay. The speed of light, sum it up, speed of light has a constant of 3 times 10 to the 8th meters per second. The speed of light remains constant in all inertial frames. That means that nothing can go faster than the speed of light. And this has been proven over and over and over again because we have not been able to accelerate a particle to go faster than the speed of light. And then this realization led to the 2 postulates of special relativity. Okay.